Good afternoon, everyone. So this is Emmanuel, and the reason I'm making this video is because of the little time we have left to spend with one another. And with the load of work on the field, it is necessary of me to do this. So this will be a continuation of our class or conclusion of our class. So I'm just going to run through this slide. This slide should cover fertigation and its management. Remember, we are taking baby steps. So you might want to ask, when do we stop taking baby steps? So one thing about agronomy is you never stop growing. You never stop growing. So in this slide, at the end of this slide, there is a question that someone has attempted that I dropped on a Telegram group. But let's just quickly go through what we have in this slide: fertigation and its management. So to start with, we will be looking at the classification based on nutrient contents. Classification based on nutrient contents. And in that light, we will look at straight fertilizers and compound or multi-nutrient fertilizers. So straight fertilizers just mean the fertilizer you apply to your plants, but this time around, they only have a target nutrient. So they are only supplying a primary nutrient, unlike multi-nutrient fertilizers that we are used to. So if you check the picture that is associated to this slide, this is a common fertilizer, 19-19-19. So it could come in form of 15-15-15. So this is a typical polyfeed fertilizer, multi-nutrient fertilizer. But in straight fertilizer, unlike having 19-19-19, you will just have one nutrient. That is, it is supplying one nutrient. An example of that is the SSP, the single superphosphates, supplying phosphates singly, triple superphosphates, and the likes. That is for soil application. Then for soilless application, you are dealing with something that can easily be dissolved. So in that light, we are looking at potassium hydroxide and the likes of phosphoric acid, nitric acid. So for compound fertilizer examples under soil application, we have your DAP, you have your gypsum, you have your NPK 15-15-15. The NPK just means you are getting nitrogen from this compound, you are getting phosphorus, and you are getting your potassium. Now for soilless application, you can also have this. We would expatiate on that later. You can also have this. You have MAP, you have MKP. Now this just stands for monoammonium phosphates, MKP, monopotassium phosphates. Then you have your calcium nitrate. These are not only supplying potassium as in the straight fertilizer, but they are supplying phosphorus, potassium, calcium, as the case may be. So to move on from this slide, so this slide is just there to give us heads up on some things to take note of when doing fertigation. So in integrated plant nutrition, you have your singular fertilizer, your straight fertilizer, you have your multi-fertilizer. In integrated plant management, we are looking for ways to make use of these two together to achieve a particular result. So in this slide, let's go back to the last slide. Now, most of the time in soilless application, we do make use of phosphoric acid as a step down component. That is, when you have a buildup of salts in your substrates, phosphoric acid is added to step it down. When you are approaching a pH that is more than 6 or more than the required pH for a plant, you add phosphoric acid, which is a straight fertilizer, and you have been using, say, for instance, calcium nitrate, MAP, potassium nitrate, and the like. So in integrated pest management, how can you combine this together to give your plant what it needs? So moving on. It is also important to know that under and overnutrition is detrimental to the health of your plant. So a man, you have obesity and you have malnutrition. It is the same with plants. It is the same with plants. It is the same. In the last class, we discussed law of limiting factor, where when one element is missing, it affects all other elements. It affects the overall nutrition. It even serves as a gateway for pests and diseases to come at your plants. So moving on from there, we'll look at fertigation in broader light. So the term fertigation refers to the application of fertilizers with irrigation water. So with irrigation water means you are making use of comprehensive irrigation systems that supplies irrigation to your plant, that supplies water to your plant. So that term is called fertigation. In some literature, you can get the word nutrigation, as in N-U-T-R-I, which is also the same as fertigation. And this has a lot of advantages. One critical advantage is that it saves time and energy. It saves you time and energy. So compared to the conventional way of irrigating your plants, where you make use of watering can, buckets, big bowl, to singly give your plants nutrition. So in this slide, when you are supplying the whole plant at the same time, which saves you man labor, saves you time, saves you energy. So it makes you very flexible with nutrient application also. It makes you very, very flexible. So it allows you to calculate correctly the amount of fertilizer that you are applying per time, So the nutrient you supply when you do that can be monitored with precision. So fertigation is applied through the drip irrigation system. Thereby, the surface of your plants is kept dry. So that's as a way of controlling pests and diseases. So fertigation has a function in pest and diseases management. Fertigation has its own role in controlling pests and diseases. So moving on from there, we look at the substrate texture when applying fertigation, or when applying fertilizer, or when passing nutrition through our comprehensive irrigation system or our secondary lines. That is the drip tapes, the drip tubes, the porous pipes, and the likes. So the substrate texture is very crucial for determining the volume of nutrient solution to distribute for each application. What this just means is substrate texture is one of the physical attributes or characteristics of your medium for growing. That is the substrate you are using for growing. What is the texture like? How accommodating will it be to take in nutrients. Take for example, let me use an analogy. If you have a sponge with plenty holes and you have a sponge with, say, a foam, you are using a foam as a sponge, the rate at which they soak in water will be very different. Now, your normal sponge, say the one that is made from, I can't remember the name of the leaf now, but the normal traditional sponge, when you pour water in it, it has a way of allowing water escape faster than your foam. They are both used as sponges, but the rate at which they soak in water, the rate is different. So extrapolate Rhizol and biochar for your traditional sponge, that is the one made from wood. So you have a lot of escape. So in this light, you are required to apply more nutrition per time if you are using, say, Rhizol and biochar, because they easily allow the escape of fertilizers, hence leaching. Unlike fine textured surfaces like soil, like cocoa peat, like loamy soil, like cocoa peats and the likes, that takes in nutrients and for a longer period of time. So another concept to look at, this is a chemical characteristics. While the substrate texture is a physical characteristics to take note of when irrigating or fertigating, the CEC is a second chemical characteristics to take note of. So the CEC stands for the cation exchange centers. Cation exchange centers. It just means how charged, how accommodating will your substrates allow nutrients to be attached to it. So for example, cocoa peat has a more charged surface compared to Rhizol. The exchange centers in cocoa peat is more than Rhizol's. Hence, it has a surface area to suck in ions from your nutrients and the likes are in form of elements. So when you dissolve them in water, they fly about in form of electricity, in form of electrons, in forms of elements. So those are analogies. So moving on from there. So the basic components of a fertigation system, just like we will have here, the basic components of fertigation in any fertigation, just basic. Now, fertigation is relative. Your system is relative. The richer you are, the more bulky your system will be. So, but basically, you would have a stock tank for fertilizers. You always have a stock tank. If you go on Google, you browse it, you'll see how they do arrange their tanks. So tanks come in different formats, but you do have a store tanks. Then you have a water source. So your water source could be your, like we're building here, your reservoir, your borehole, just a water source. Then some growers or most growers make use of injectors. Don't worry, I would show you all of this. And I know we would have a lot of time to, no, I might play a video at the end of this class. So let me quickly run through this. In fertigation management, it is critical to ensure that the fertilizer is formulated properly. So the more accurate you will be in formulating your fertigation regime, the more the more you have results from your plants. So the grower must mix the correct amount of fertilizer. In the last class, I made mention of this adequate amount. Reason being, you don't want to have toxicities and you don't want to have deficiencies. So, and I gave a range. Say, for instance, you are doing lettuce. So there's a range your nitrogen must fall into. There's a range your phosphorus must fall into. There's a range your potassium must fall into to have a healthy plant. Overnutrition and undernutrition has a detrimental effect on these plants. So formulation with compound fertilizers often results in a mismatch with the required ratios or individual element. This is quite explanatory. It is important to have knowledge of the irrigation system established for the greenhouse. That is, in a simple greenhouse, you have a primary line, you have a secondary line. A primary line is also called lay flats. So lay flat is what supplies water to the secondary lines. The secondary lines are your typical drip tapes, drip tubes, porous pipes, while your lay flats can be, in some cases, you make use of pipes, maybe 1.5 inch or 2-inch pipe that carries water from your tank or from the water source or from the nutrient source, as the case may be, whether you are doing nutrient solution or stock solution. Then, yeah, that is that about that. Then this is just to, we are slowly progressing. We moved from fertigation. Now we are extending to how to utilize this in the calculation of the crops that will be in our house. This will have a resultant effect on how we schedule our water management. So in this, say for example, you have a 10 by 50 meter of spacing for your greenhouse, and in this you have 12 emitters, 12 drip lines, that is 12 secondary lines. You have one primary line. This one primary line is connected to 12 secondary lines, and in these secondary lines you are making use of 40 centimeters. 40 centimeters. In doing this, you have about 1,500 emitters in a 10 by 50 meters house. This is the usual case for bell pepper, tomatoes, cucumbers, and any other fruity veggies that you want to put in your greenhouse. You can decide to use 40 centimeter spacing, that is between one plant to another plant. You can decide to use 50 centimeter. Some people go as far as using 60 centimeter. What this does is it helps you manage your plants properly. The farther your plants are from each other, from one another, the farther the rate of infection will be. So the closer they are, the closer they are likely to spread pests and diseases. So on average, in a typical, the typical recommendation for plants is the typical water requirement for your plants is for your plant to get 2 liters per day. 2 liters per day. 2 liters per day. Then you can schedule it as you want. You can break it down into say you want to feed them 5, 6, 7 times in a day. So you can divide that 2 liters into 5. You can divide it into 8, depending on the stage of the plants. Growers must accurately determine the amount of fertilizers. So we have moved from the component of irrigation, fertilizer, what is necessary for your plant to grow. We have discussed the substrates and the secondary fertilizer. Now we are moving to fertilizer mixing for growers. So we are slowly progressing in that light. Growers must accurately determine the amount of fertilizer needed to mix stock solutions. So we will look at stock solution in the later slides, still in this lecture. Most of the manufacturers of commercial fertilizer and fertilizer injectors rather, have produced tables that simply. So when say for example, I'm not marketing any group, you want to purchase fertilizer from IFA Group. IFA Group makes different fertilizer mixes. They have 19-19-19, they have 15-8-33, depending. When you go on their website, they will give you, they have tables, they have recommended ppm, milligram per liter, that is to be supplied to the plants per time. So sometimes you don't need to bother yourself with this if you have a competent agronomist. His work is to formulate this and mix it in proper ratios. Growers can make use of formulas to calculate the amount of fertilizer needed. If the rate of fertilization to apply to the crop, the percentage of NPK in the fertilizer and the injector ratios are all known, then the calculation are simplified by the formula. So I intentionally removed a formula from here just to teach you in later series, or to show to you in later series. I can drop it at the end of this slide also. So moving on to nutrient solution. So in this we didn't discuss, but we made mention of stock solutions. So let's look at nutrient solutions. So to simplify, nutrient solution just means there is no dilution factor. You just have your overhead tank, you mix your nutrients, you pour it in your Storex, your GP, or any brand as the case may be, then you give it to your plants. So with large volume tanks, we only those fertilizers needed per batch. So every time you need to apply fertilizers, you mix it, you dissolve it with water, then you pour into a large volume tank. This large volume tank has been connected to a primary line that connects to your secondary lines. So in preparing nutrient solution, some of the bullet points are as follows. Fill the tank, the nutrient solution tank, with water to about 1/3 full. Dissolve with fertilizer and stir vigorously. Dissolve the macronutrient first, then the macronutrients. This is necessary because you don't want some binding effects to occur. Then pour in differently the sulfate and nitrates. Pour in separately sulfate and nitrates. Again, you don't want binding effects on your plants. Also, after that, you then pour your micronutrients. Check the pH and adjust. So your plants pH do well between that range of 5.5 and sometimes 5.8. You can extend it to 6.0, and as far as 6.7 is still within range. With this range, you are not at the risk of having deficiency and toxicity. So moving on from there, we have calculation of nutrient formulas. So if a nutrient formulation calls for 200 parts per million, that is milligram per liter of calcium, that is, you need it. You need 200 parts per million of calcium. What it means that in every liter of water, 200 milligram must be inside. So to cut the long story short, without doing our molar mass calculation and all, you have the weight of calcium nitrate to be 164 milligram. That is, if you have to reduce yourself or become an ant-man, all right, and you take a mole of calcium nitrate and put it on a scale, right, you will get 164 milligram. So in 164 milligram of calcium nitrate, there's a reason why I'm slowing down to explain this. In 164 milligram of calcium nitrate, you have 40 milligram of calcium. That is, in your calcium nitrate, which is, this is the formula, you just have one calcium molecule. Your nitrogen is 2, while your oxygen is 6. This 2 subscript 2 just means that you have nitrogen here to be dimolecule or bimolecule, but your calcium in essence is 1 molecule. So what is the atomic mass and molar mass of calcium? You have it to be 40. You have it to be 40. Most of the time, the atomic mass of oxygen, nitrogen are usually different from their molecular mass because they are diatomic. So we have 40 milligram, but our focus is getting 200 ppm. So when you do your cross multiplication, you understand, you have 164 parts per million of calcium nitrate to give you 40 milligram of calcium. So how many milligram of calcium nitrate will be required to yield 200 milligram of calcium? You do cross multiplication. At the end of the day, you find out that it requires you to get 820 milligram of calcium nitrate to yield your 200 ppm. This is simple because you are not dealing with stock solutions. This is the calculation if you are doing nutrient solution. So moving on from there. So in adjusting your nutrient formulation, because they are not constant, you have different stages of plant growth. So these different stages of plant growth commands different nutrient application and formulation. So your plant species and variety, lettuce or cabbage requirement for nitrogen is quite different from bell pepper requirement of nitrogen. The stage of plant growth, when plants are in vegetative and generative state, they command different nutrients formulation. The part of the plant that you want to concentrate on, the weather, temperature, and the likes, atmospheric environmental conditions also determine the nutrients you apply per time. So moving on, we are done with, we browsed through, we skimmed nutrient solution. So let's talk on stock solution. So in stock solution, you have a concentrated mixture in a, I don't want to use the word bucket, or in a container, a concentrated fertilizer solution in a container. And you do not need a big tank. You just need a small concentrated fertilizer to be in a very small bucket. And in this small bucket, you increase the strength. So you have a source of water and you have a small bucket. Now, in that small bucket, you have fertilizers. Your stock solution and your nutrient solution will still give the plant the same thing. But in this time around, what you are trying to do is you are limiting the amount you are spending on buying big tank. So in doing that, you increase the strength, that is the concentration of the nutrient you want to apply to your plant in that small bucket. So in doing that, a water meter monitors the flow, measures the flow of water. A water meter monitors the flow. So we have things like, we have meters like the flow meters that gives us the flow of water, the liters that is leaving the, say for example, the reservoir, your source of water per time, and is that is mixing with the stock solution, that is the concentrated solution. Now, the concentrate is held in small containers, just like I said. 2S and 2 concentrate, that is, you will have them in 2 separate buckets. This again is to prevent them from mixing at any point in time. This is necessary so calcium does not combine chemically. So in this chart, you will see fertilizer compatibility. In this chart, you'll see fertilizer compatibility. In areas where you have green, they are compatible, but when you have orange, they are not compatible. For example, you have your nitrates and your phosphates. Calcium nitrate and MAP are not compatible. When you put them together, they create binding effects, block your irrigation system, especially your secondary irrigation components, and you would have to replace them at the end of the day. You have to replace them at the end of the day. So again, time is running out. It is important to know the injection ratio. So in the question after this, you have 1:100, but you can also have other ratios like 1:9. That is, the strength is 1:9, is 9. This 1:16, 1:100, 200, as the case may be. So to adjust your nutrient solution, you make use of different meters such as your pH. You make use of your TDS, EC meters. So EC meters is measured in micromoles or microsiemens. Your TDS is your total dissolved solids, which is also measured in ppm. Then you have analysis of how to turn your phosphate into phosphorus for easier calculation. This is me trying to bring shortcuts to you. So for your percentage phosphorus, when you have your phosphates, you will divide the percentage. Say you have 56% of phosphate in a secondary fertilizer, you divide that by 2.3. Then for, as the case may be for K2O, then question and A, you have this. You have this. With this, we have come to the end of this class or lecture. This is just to make up for the time that we've not spent together. This is just to make up for the time that we've not spent together. So if you have any question, you can reach out to me. I will make more videos like this. I hope this is explanatory enough. If it is not, please just let me know. Just let me know.